Okay, in this video, I'll be proving that for any group G, if H or K is normal in G, and H and K are both subgroups of G, then HK is a subgroup of G as well. So for this proof, you can start by either choosing H to be normal to G or K. It doesn't really matter. The proof is the same either way. It's just up to you, really. So, for this proof, you're going to need to do three things. You're going to need to show that HK is a subgroup of G, HK has closure, and HK also has the inverse property. So to show that it's a subgroup of G, it's kind of trivial. That's because let's take HK, let's let HK be in HK. Well, we know H is going to be in G because H is a subgroup of G, and we know K is going to be an element of G because K is also a subgroup of G. And so H operate K is going to be in G because both those things are already in G, and G is a group. So that's kind of trivial. The closure, I'm not going to go over the closure. That's kind of a thing on its own. So I'll just be proving the inverse property of this thing. So partial proof. Oh, come on, work with me. Damn, stylus. So I'll just be going over the inverse property here. So consider, well, let's let this happen first. Let HK be in HK. So consider H inverse K inverse. This is what we want to exist in HK. We just need to show that this is true. Okay, so we also can say, we also know, notice that H inverse K inverse equals K inverse H inverse K. Let's slap some parentheses around that, and K inverse here. Right, this is true. Oh wait, this is backwards. This should be, wait a minute. Notice K inverse H inverse. Oh. Oh. Erase all this, forget all this. Consider this. K inverse H inverse, sorry. This is what we want. Because if we operate HK with K inverse H inverse, this is how we're going to want it to collapse. This is basically going to collapse on itself. These, because K operate K inverse, is going to turn into the identity. So we're going to get H, E, H inverse. The identity is basically just kind of like multiplying by 1, so we can kind of get rid of it. And then we're going to get with H, H inverse, which just turns into E. So that's why we need it in this order. Because if we had it like this, if we had this order that I originally had on accident, if we had H, K, and H inverse, K inverse, we don't necessarily know that these have the don't necessarily commute, so we don't know that order doesn't matter. Like for instance, in multiplication by the integers, we know that commutes, right? Because 2 times 3 times 4 is going to be the same thing as 2 times 4 times 3. But in this instance, we don't know that this is true. So that's why we have to have the k first. So let's go back here. Consider k inverse h inverse. And we know that this, notice k inverse h inverse is equivalent to k inverse, it's really bad, k inverse h inverse H parentheses K inverse. No, this is supposed to be a K. Sorry, this should be a K. And then we have a K inverse over here. The reason this is true, right? This K here, these two K's on the outside, this K inverse, they're going to collapse, turning into E, and then we're just going to get left with the K inverse, H inverse again. So what do we do with that? Well, we know since H is normal to G, we have GH G inverse is an H. And for all G and G and H and H. Sorry, I should have these little operators here. Furthermore, for all K and K, K is in G. That's because I'm letting K, K is a subgroup of G. That's already in the hypothesis. So we can kind of replace those G's here for our normal definition. We have thus K H K inverse is an H. So that takes us back to here, this KH K inverse that we're considering, or K inverse H inverse K inverse here. We've just figured out that this is an element of H. Now we just need to show that this K inverse is an element of K. Oops. Is an element of K. And if we've done that, then we're done with the proof. So, well, we already know that K is a group. So since K is a group, we already know that K is has the associative property, has closure, and also has the inverse property. So also K inverse exists in K because K is a group. Reason K is a group is because it's a subgroup of G, and to be a subgroup, you already have to be a group itself in yourself. I guess it's time for a new page. So K inverse H inverse K inverse exists in HK. And so there you have it. HK has the inverse property. Come on. The inverse property. And so that's 1/3 of your proof that you're going to need for the whole thing. So there you have it.